for this. The first thing I have to say is that for some reason, once again, Zoom failed to record the lesson from yesterday about one variable Taylor functions. And so I promise I will record a replacement video for that, like a 20-minute boil down of how one variable theory works. And then I'm kind of sad the whole discussion about why a Red Bull can is the size that it is didn't make it onto video. I don't know why Zoom ate that. So I apologize. I will go through that again so that we have a recording of it. And then, yeah, so let me just sort of briefly reorient us on where we're doing. In fact, I might turn off this share and show you kind of what's going on. I can pause this, I think. So, no, that's not what I want. How do I turn this off? Stop share. Okay, so let's go over here to, oh, those of you that have been sick, by the way, I noticed there's multiple people here that have been sick. I hope everybody's feeling better. Those of you that expressed concern about my son, he is extremely tired, but he's breathing well right now. So can you see a copy of Colley's book up on the screen right now? Am I sharing this correctly? Okay, so let's go up here to Math 3D. Maybe not even Math 3D. Let's do it old school. Let's go to Desmos. Okay, so let me show you like a sort of a graphical, like what I was talking about last time, a graphical representation of exactly what it is that a Taylor series does. So to begin with this, let's look at y is equal to the sine of x. That's a good place to start. And let's just start building the Taylor series for this and see what it looks like. And we can pick any point we want, but one place to start would be to start writing the Taylor series for sine looks like this. So I happen to know that the sine looks like x. So there's that right there. That's P1, right? So this right here, that is P1 for this function. P1 is the line that approximates the curve. And it's a pretty good approximation, right? I mean, if you look at that, in fact, that's kind of shockingly good approximation for the sine, that you can get away with the line y equals x for so long here. I mean, you can see the blue line and the red curve are really close to each other. But suppose you're not happy with that and you want to use a higher Taylor polynomial. If you go one step further and you do the next term in the sequence, then you get this cubic function, which is even closer to the curve than the line was. Now we're matching not only the original tangent line, might as well add that in there. Here's the original tangent line. So you have an original tangent line, but now you've got this cubic Taylor polynomial. So this is the degree 3 Taylor polynomial, and that degree 3 Taylor polynomial matches the sine even better than the green line did. So the blue line is the third order approximation, and it hugs the curve even more tightly. And as you continue adding more terms to this, oh, not 5, it should be 6. There, that's even better. If you add more terms to this, you continue getting a better and better combination. So then if you add x to the 5th, and then what's 5 factorial, 120, you can see that as you continue the approximation with more terms, that where that approximation is good travels down the curve so you get a bigger area that the approximation is good, and also the approximation gets better and better. So by the time we get to a 5th degree polynomial here, I want you to notice that between 1 and -1, so if we just really zoom in on 1 to -1, the blue curve is the sine. The purple curve was our 5th degree polynomial approximation for it. And I've got to say, looking at that 5th degree approximation is basically the same as the function. Okay, so Taylor series basically are built to approximate functions. Now, in 2 dimensions, this is weirder. So I'm going to show you an example of what a 2-dimensional approximation looks like first, and then we'll talk about how we get it. So I'm going to come over here. I guess I have to go to the Canvas page because I don't have the thing set up, and go to the class and go to modules and go to Taylor approximation. Go to this. Okay. All right. So this is a two-dimensional surface, or this is a surface, right? This object right here is the surface that looks like this. So 1/4 x to the fourth minus x squared minus 1/4 or plus 1/4 y to the fourth. That's the surface. And the idea is that if I want to, I could approximate this thing with tangent planes pretty easily. So the way that would look would be I just calculate the partial derivatives. I could set up a tangent plane, but that's not a very good approximation in the same way that a line approximation is not a very good approximation for, here, let's actually get all of this, and I'll steal this for a second. Let's turn this on. So as I slide the sliders around, you should see what's happening here is that the point is telling you where the approximation is happening. So this point right here tells you where the approximation is happening. And if you turn to the side, you can see that plane is doing a pretty good job of describing how that function is behaving as it comes around, right? The linear approximation looks pretty close to the function. You guys have seen examples of this before. I've shown this example. If we come around here and we go to, say, like one of these butt points down here, you can see that here where it curves, this tangent plane falls away from the graph pretty quickly, right? There's gaps between the tangent plane and the function that it's approximating, but at least close to the point, the tangent plane and the function are very similar. So what we'd like to do is this. So this is the paraboloid that approximates the surface at that point. In the same way that there's a curved line, a second-degree Taylor polynomial or a third-degree Taylor polynomial that approximates a graph more closely than a line does, I'd really like to be able to come up with a way that I can approximate this function in lots of places with a function that looks like this. And you see, as I slide this point around, this paraboloid that's approximating the function is a lot closer to approximating the function as a curved object than the flat plane was, especially places where that function curves a lot. So at this point right here, where I have the slider, it should be pretty obvious to you that if it was a flat plane right there, the curve would kind of sit on it and then peel away from the flat plane really, really quickly. But if I allow myself to have a curved surface, it can sort of like squish up against the surface in a way that makes this approximation much better and it works on a larger region. And you can slide this thing around and you can see that, like, you know, in various places at the dot right there, if you look from the bottom, you can see that that tangent approximate, or sorry, not tangent, that second degree, that quadric approximation for the surface is pretty good. I'll give you another example here. This one is this, just kind of a gnarly looking surface. That's a product of cosines, right? So that's cosine x times cosine y. So it kind of cosine in two variables at the same time, super lumpy. And if you turn on a point, you can track a point around the surface here. Where's my point? There's my point right there. I can slide it. This, I believe, is a tangent plane approximation. So tangent planes do a reasonable job. I mean, they kind of show what the function is doing. If you go down here, you can see that they measure slope of the function. And if you zoomed in really close to that point right there, the tangent plane is pretty close to behaving like the function does. But boy, oh boy, would this approximation be better if it could be curved, right? A curved surface would be a better approximation for something like this than a flat surface can be. And that's the point of what it is that we're trying to do. I don't want to approximate just with a tangent line. I would like to approximate with something that curves with the surface. So this is the second degree approximation for that surface. I don't know why I chose that color. It's terrible. Here. That's just as bad, but at least you can see it's different. So you can see that that surface, I'm claiming that after we're done today, you guys are going to know how to come up with what this thing is supposed to be. That surface right there, you can see at that point just sits right down inside of the surface that we're trying to approximate. So at least in this little bowl right here, we have a much better approximation for what the surface defined by these two cosines is doing. And as I slide the point around, you can see that the approximation changes. So here, our approximation is also a quadric surface, but it points down. And as I move this thing around, you get different values out, different kinds of surfaces come out. This is kind of a weird one because why is it twisting like this? Why is the surface twisting as it rolls? Well, if you look at what the blue surface, the cosines are doing, in one direction they're moving one way, and another direction they're moving the other, and that gives you kind of this twisting saddle type setup that we're looking at. A plane cannot account for that, but a quadric surface can incorporate these sort of twists. So these are much better approximations locally than tangent line approximations are. So this demo is set up on Math3D. You can get to it from your Canvas page. And now I'm going to go over to my iPad here. If you'll let me put up with having me switch back over again, and we'll go through how these things are produced. These are some of my favorite objects that exist in mathematics here. So I'm pretty excited to be able to show you guys how this works. Let's go back to OneNote here. And of course, if you have questions about any of these things, or you want to know how to generate these pictures on your own, please come in and ask me about that. I think it's really useful to be able to get me out of here. It's pretty useful to be able to visualize why these things are happening the way that they are. So I'm going to ask you to recall that that we define the polynomial in one variable. So this is the one variable case. That we had pk of x was equal to f evaluated at a plus f prime evaluated at a times x minus a. And we keep doing that until we take the kth derivative of f. We evaluate it at a, we divide by k factorial, and we multiply by x minus a to the k. Okay, so that's our, these are called the kth Taylor polynomial. And in particular, I want you to pay attention to this one. P2 of x is equal to f of a plus f prime of a times x minus a plus 1/2 of f double prime of a times x minus a squared. So the second Taylor polynomial involves second derivatives because that's where you pick up curvature. This gets you the function value. This gets you tangent. And this gets you curvature. Where we left off last time was in the linear version for multivariable functions. So last time we said that for f that takes a domain in Rn to R, so an n variable function instead of a one variable function, that we defined P1 of x to be equal to f of a plus, okay, well, there's not just one derivative, there's n derivatives. So we define that to be the gradient of f at a dotted with the vector x minus a, or in matrix notation, f of a plus df a times x minus a. And of course, this wasn't new because these are just the tangent planes. This is tangent planes. All right, questions so far? All right, so if I want to make this work in lots of variables, I need to involve second derivatives. The problem is there's lots of second derivatives. So let's just suppose for a minute that we're going to build this formula. Let's restrict our attention to just functions f that take in a variable x and y. So a two variable function. How on earth am I going to build this thing to involve second derivatives? Well, what are the second derivatives of f? Well, I'm going to have f of x, let's write this down. I've got my first derivatives, fx and fy. And then I've got second derivatives that look like fxx, fxy, fyx, and fyy. There's lots of second derivatives for a two-variable function, right? Two-variable function has 4 second derivatives. And yes, it's going to turn out to be the case that the mixed partials are equal, but we're not doing that quite yet. Okay. What we want is the following. I want to define a function p2 of x that has the following properties. I want it to be the case that p2 of ab is equal to f of ab. And I want it to be the case that d by dx of p at ab is equal to fx at ab. And I really want it to be the case that d by dy of p at ab is equal to fy at ab. You remember, when we built Taylor polynomials, the idea was that we wanted all the derivatives to match. This thing right here was the only first order polynomial that had the property that p of a is equal to f of a, and that d by dxi p at a is equal to d by dxi f at a. All of the partial derivatives matched. Okay, first partial derivatives. And that's the unique polynomial that had those properties. Now we want to have a second order polynomial that satisfies the function value, the function tangents, and also the curvature of the function, which means I want to be the case that d2 dx dy of p at ab is equal to d2 dx dy f at ab. The same thing in reverse. D2 dy dx. And then also the unmixed partials, d2 dx squared p at ab had better be equal to these guys. dy squared p ab is d by dy f d2 at ab. So the idea here is that all of these things together, these measure the sort of curvature of a surface. The second derivatives are going to tell you how locally that tangent plane should bend if it's going to try to match the surface. And so in my demo, what I did was I actually computed those things and built them into a polynomial. And the idea is that there's one single polynomial that does this for a two-variable function, and it looks like this. So there's a unique polynomial that does this, and it's p2 of x and y is equal to fab plus fxab times x minus a plus fy ab times y minus b. That's the same as the tangent plane approximation so far. Now we're going to do the part where the function has to curve. fxx at ab times x minus a squared. So this is important that the x minus a's have to go along with that second derivative to match. We want that second partial in x to match, so it has to be tacked on with an x minus a squared. We're going to have another term. Oh, and also because that 2 is going to come down, there still has to be this 1/2 out front that's also in the original Taylor polynomial. So there's a 1/2 right here. There's a 1/2 fyy.
Shouldn't it be P2 AB?
P2, no, because P2 is going to be evaluated at an x value and a y value. The AB, there's a unique polynomial near the sort of anchor point. So the anchor point is the point AB. AB is like the fixed point where we lock down our approximation. So AB is some fixed point on the surface, and we're going to compute all the partial derivatives there. But then what the x and y are going to say is that's what's going to give us the quadric surface, right? So the variables are x and y. Y minus b squared. And then we've got these mixed terms that look like 1/2 f xy at ab times x minus a, y minus b, and then 1/2 fyx at ab, x minus a, y minus b. But by Clairaut's theorem, sufficiently nice functions, these things are the same. And so normally we just combine them together, because normally f of xy is going to be equal to f of yx. Remember, that's if f is a C2 function. Then the mixed partials will be equal. But man, you know what? If we're going to do this in more variables, we're going to need a better formula because this is awful. I mean, this is just a 2-variable function, and look at this monstrosity. Look at all the terms this thing has. It's a lot of terms. And you can imagine with 3 variables, there'd be even more mixed partials running around, which means even more terms just to get this sort of curved surface approximation. So what we'd really like to do before we move on to the general formula is to try to figure out a way to write this down that is not as ugly as this. And really what that means is I know a way to organize the first partial derivatives, right? The first partial derivatives are easy to write down because we had this thing df. And df at AB is equal to df dx at AB, df dy at AB. So the matrix of first partial derivatives, that's just representing this term and this term right here. And we use this all the time when we write down that the Taylor approximation is P1 of x is equal to FAB plus DF at AB times x. In fact, we should be more clear than that. Maybe I could just write xy minus AB here. xy minus AB. I mean, this is much easier to write than a monstrosity like this. So now the question becomes, how can we organize the second derivatives? Because right now, the second derivatives, I mean, 3, 4, 5 variables, there's going to be millions of second derivatives. So dfab organizes the first derivatives. Of f. So we're going to introduce a new object that's going to organize the second derivatives. And this object is one of the central objects of optimization, of working with functions in more than one variable, in any sort of like approximation theory, and it is called the Hessian matrix. So the Hessian, or Hessian matrix, of f that takes a domain in Rn into R is the matrix with ij entry equal to the second derivative of f with respect to xj, xi. So that means we could write the Hessian of f is equal to d2f dx1 squared, d2f. Oh, you know what? Forget this notation. Let's use better notation. Who wants partial differentiation? It sucks. Ugh. Do it this way. fx1 x1, fx1 x2, out to fx1 xn, and then fx2 x1, fx2 x2, out to fx2 xn, all the way down to fxn x1, and then all the way across to fxn xn. So it's the matrix of second derivatives. So let's do a quick example of how to compute one. So suppose we've got the function f of x and y is equal to x to the third y squared. Then df is equal to 3x squared y squared, 2x to the third y. Because remember, this is fx and this is fy. I'm on about 4 hours of sleep, so if I make computational mistakes, make sure you speak up and yell at me. Okay, that's df. What's hf? Well, HF says the first row of HF is going to be all of the different derivatives that exist of fx. So we should get fxx and fxy in the first row. So the derivative of this with respect to x is 6xy squared. And the derivative of that same object with respect to y is 6x squared y. The second row should be the derivatives of fy. So this should be fyx, and this should be fyy. Now, if we've done this right, this will be a symmetric matrix. So if I take this and I take its x derivative, I get 6x squared y. It's pretty reassuring that these are equal to each other because Clairaut's theorem says they should be. And then the second derivative, the two derivatives with respect to y gets us 2x cubed. And so this object is the Hessian. Now, just to point out here, if Hessian rings a bell because you've recently been studying in history class about the American Revolution and how like the Hessians were German mercenaries that like fought in the Civil War or fought in the Revolutionary War, this is actually not what this is named after. There's some dude named Hesse who invented this thing that this is named after. So it's not named after German mercenaries. I actually was going to point that out anyway, but then I noticed Kali actually does it in the text. So okay. So let's see if we can figure out a way that we can use the Hessian to organize the second Taylor polynomial in a more useful way. This, but so that the Hessian is like super useful object. It might seem like an artificial thing to have invented, but it's actually very, very useful for computation. So let's actually, for this function we just wrote, for this function, let's see if we can write down this polynomial, this P2F thing right here, this monstrosity. We're going to write this down for that function. And let's do it at the point 1, 1. Okay, so if we have f of x and y is equal to x to the third y squared, and I want to write down P2 at the point x, or sorry, a is equal to 1, 1, then I'm going to need a whole lot of derivatives to be evaluated. So here's what I'm going to evaluate. I need f of 1, 1, which is 1. And I need fx of 1, 1, which is equal to 3x squared y squared evaluated at 1, 1, which is 3. I need fy at 1, 1, which is 2x to the third y evaluated at 1, 1, which is 2. And I need fxx at 1, 1, which is 6xy squared. See, already up here, I can just go up here and read off what these are if I know what the Hessian is. So it's 6xy squared evaluated at 1, 1, which is 6. And fyy at 1, 1 is 2x to the third at 1, 1, which is 2. And then fxy is equal to f of yx, which is 6x squared y evaluated at 1, 1, which is 6. Okay, so how do I turn this into the polynomial P2? P2 is supposed to be f at 1, 1 plus fx at 1, 1 times x minus 1 plus fy at 1, 1 times y minus 1. I'm only ever going to do one of these, by the way. So if this seems long-winded, it's just as long-winded for me to be walking through this example. Plus fxx at 1, 1 x minus 1 squared, with the 1/2 out front. And then because I'm going to combine that yx and the xy term, I'm going to leave off the 1/2. And that's going to get me 6. Wait, nope, I can't skip that yet. That's f of xy at 1, 1 times x minus 1, y minus 1 plus fyy at 1, 1 times y minus 1 squared. Ugh. But at least once I have the numbers, it's pretty easy to write down. This is P2 is 1 plus 3 times x minus 1 plus 2 times y minus 1 plus 2 times, no, this guy right here, I guess is next. So that is 1/2 times 6 times x minus 1 squared. And the fyy term is 2 times y minus 1 squared. And then I have to add on the mixed term, which is 6 times x minus 1, y minus 1. So that dude right there, that's your second order Taylor polynomial. But man, oh man, it would be nice if there was another way to write this. So it turns out to be the case that if you think about this for a second, let's take a look at just this part. 1/2 times 6 times x minus 1 squared plus 1/2 times 2 times y minus 1 squared plus 1/2 times 6 times x minus 1 y minus 1 plus 1/2 times 6 times x minus 1 y minus 1. It doesn't look like a dot product like the other thing does, but if you look at this for a minute, you should be able to convince yourself that what's going on here is that this is actually, you can write this in this form. This is 1/2 times the vector x minus 1, y minus 1 times a matrix that looks like 6, 6, 6, 2 times the vector x minus 1, y minus 1. So the idea here is if you actually multiplied this out, you would get this back again. And this is the Hessian matrix of F evaluated at 1, 1. And this is a vector x minus a. And this is the vector x minus a, but tipped over into a row vector. So we put a transpose on it, which tips it over into a row vector. And then all of that has a 1/2 out front. So all of this right here is a very, very shorthand way of recording what happens with all the second derivatives in a nice condensed form. So the Hessian matrix actually tells us how to write down the quadratic terms of a Taylor polynomial, second degree Taylor polynomial. So I'm going to make this more clear in a formula which says that this is the big claim, P2x is equal to f of a plus dfa x minus a. And then the second order term, which looks like 1/2 x minus a transpose hfa x minus a. And that guy right there, that's how we use the Hessian. So the Hessian matrix, the matrix of second derivatives, the fact that that matrix exists allows us to write the second Taylor polynomial in this extremely compact form. So in symbols, what that would mean is the following for, say, a 2-variable function. So if we have a 2-variable function, it means that P2 of xy is equal to f at AB plus fx at AB, fy at AB times x minus a plus 1/2 x minus a transpose fxx at AB, fxy at AB, fyx at AB, fyy at AB times x minus a. So when you're doing, you might say, "Oh wow, what a grand thing you've done to have turned this very simple idea into this compressed notation." But remember that typically the functions that we're dealing with in practice, when we're working with these things, could have thousands of variables. In which case, having a very succinct formula for what it is that you're working with turns out to be really important, because the Hessian matrix could be 1,000 by 1,000 or 2,000 by 2,000, depending on the application that you're working in. Okay. So let me give you one more example here.
I have a question.
Oh, please.
All right. The thing that we're calculating right now, the P2, what is that again? Like,
This
is
is
that
the
calculating the curve?
this is the second order Taylor polynomial.
And that allows you to calculate, like, instead of a tangent plane, it's a curve.
That's that thing I showed you guys where the parabolas actually. So that's the thing that gets you those paraboloids that match the surface, right? So we didn't actually get the whole surface, but we got a paraboloid that sat right down on the surface to approximate it. So yeah, all of this stuff with the Hessian, all of this crud right here, all of
the
this
curvature of the surface.
that picks up the curvature of the surface. That's right. And actually, we can go one step further. So we're not quite here yet. So what the content of the next chapter is going to be is that I can actually use this. In fact, actually, you know what? We're going to talk a little bit about that right now. Just a little tiny bit. What do you use the second? There's a big question. What is the second derivative good for? In regular old calculus 1, what is the second derivative good for? And I want you to imagine
the curvature. What is it in like?
I mean, we've talked about curvature. What else do we use the second derivative for? I'm gonna remind everybody in the class.
Inflection point or something. What is it called?
All right. So somebody said, was that Lily that spoke right there?
I said turning points. Yeah.
Okay. So yeah. So turning points and inflection points. But I'm gonna go even more. So that's great. You guys have curvature, turning, and inflection points, but I'm going to go one step further and remind you of the idea that I'm after here. Can anybody tell me what the first derivative test is? That's an idea maybe you haven't thought about in a long time. What does the first derivative test tell you? What is that attached to? What idea is that attached to?
Isn't it to help find local minimum and maximum?
Local mins and maximums. So what does the first derivative tell you?
It can tell you when the slope of a curve is 0.
Which means that you can use the first derivative to find critical points, right? So the first derivative can tell you when slope is 0, or really secretly when slope is infinity, when it's undefined, right? And that gives you critical points. Now, where do local maxes and minimums of functions happen? Like if I'm in one variable and I'm just saying, I want to know where that function is locally maximized or locally minimized. How do I do that? Well, let's see, it's this point right here and this point right here. And those happen in places where the tangent line is like this. Oh, okay. So critical points correspond to places where the tangent line is flat, right? So if you're a local max or min, those occur at critical points. Oh, wait. Do we have a notion of first derivative that whenever it happens to be equal to 0, we could hope maybe that's going to correspond to where local maxes and mins happen? What is our notion of first derivative for a surface? What does that turn into in the several variable setting? I mean, the first derivative test should turn into something. What are we going to use here? We can't use, here we're talking about writing down f prime of x is equal to 0 and then finding such x's, right? Because that tells us what these values are. What am I going to use in several variables? What's our natural notion of first derivative?
df.
Yeah, or the gradient, right? Either way, like we want to know places where the gradient of f is equal to 0. And places where the gradient of f is equal to 0, those will correspond in several variables. That's going to give us a family of things called critical points. So this is kind of where we're building this machinery, right? Now, what is the most elegant way of deciding? Well, okay, what's the stupidest way of figuring out if a critical point is a max or a min?
Look at the slopes on both sides.
Sure, right? You just slide off to the side a little bit and see if it's increasing or decreasing and use a sign chart, right? But that's dumb. That, you know, we need a method that you can actually like lift to, like, if you had 10,000 input variables, that's not going to be very useful, right? So I'm going to ask again, what is the second derivative good for? What does the second derivative do? What does f double prime of x do at a local minimum? So I want you to imagine, okay, so I've got this function, it's traveling along, I'm at some local minimum. I know that my derivative at that point, so this point right here, say that's c. I already know that f prime of c is equal to 0. If only there was a way that I could figure out if that was a local max or a min without having to plug things into a sign chart.
Isn't
What
it
is
if the second derivative is positive or negative?
Ah, that's
maximum?
right. So that's called the second derivative test. The second derivative test tells you when a critical point is a local max or a local min. If the second derivative of c is positive, then it's concave up. But concave up means local min, right? You have to be, if you're at a local minimum and the function, if you're at a critical point, so the slope is 0 and the function is concave up, well, then you were a minimum. It's the only way it could happen. If you were at a point like this one, say that's the point D, and the second derivative of D is negative, then it's concave down, and you're at a maximum. Now, was there an ambiguous case in here? Let's see. What if I had a critical point that looked like this? I don't know. How about like f of x is equal to x cubed? I'm gonna draw a picture of x cubed real quick. Okay, that point right there. It's going to turn out to be the case that if you compute f prime of x and you get 3x squared, that f prime of 0 is 0. So 0 is a critical point. For x cubed, which means the tangent line through here is flat. There it is, a nice flat tangent line. But does the function have a local max or a local min? Well, no. It comes in, and then it just keeps growing right through that point, right? What is the value of the second derivative here?
0.
0. What does it mean when the second derivative is 0? Somebody said this earlier.
There's no concavity.
No, well, yeah, okay. And so if you go from one kind of concavity to the other kind of concavity, there's only 3 options, right? Either you were concave up and concave up, or you're concave down, up and concave down, or you're concave down and concave down at a point, right? Here, we changed concavity. We changed from concave down to concave up. And points where we change concavity are called?
Critical point.
No, critical points are about the derivative. Inflection points, exactly. Yeah, perfect. Yes, inflection points. Thank you. Multiple answers on that. So if we're at an inflection point, we get neither behavior. Okay. So how does that carry over into the 3D case? What we really hope to be the case is that we can use the same exact idea if we're working on surfaces, if we're working for the n variable functions. And that means what I would hope to be able to do, this is my hope. So what I hope can happen is that I can use the first derivative, that is the gradient of f at x, to find critical points. That'd be nice. In the same way that we use the first derivative to find critical points, because if the gradient is 0, it means the tangent line is flat or possibly undefined, right? But the gradient being 0 means you've got to, in the same way that first derivative 0 means slope 0, gradient being equal to 0 means you're flat, so flat tangent plane. And then we're going to hope that maxes and mins happen at critical points. And then we're going to hope that we can come up with some way to use the second derivative test. But of course, there's lots of second derivatives. So second derivatives to classify critical points. So instead of looking at each individual second derivative, we have to look at them all together. And so this is going to be done by looking at something about HF. So HF is going to tell us the Hessian, and the structure of the Hessian is going to allow us to classify if points are locally maximums or locally minimums. And the issue is something happens here in two variable, in say even in surfaces in two variables that can't happen in the one variable case. So in two variables, so say for a function z is equal to f of x and y, you can get points that look like this. Well, that point right there at the bottom, that has gradient of f equal to 0. That's a local min. And this has gradient f is equal to 0. That's a local maximum. And notice that on these surfaces that there's a parabola that goes this way, which is concave up, and a different parabola that goes this way that's concave up. And here we've got a parabola that's concave down, and here we have a parabola that's concave down, right? So the two different directions give us concave up, so I must be at a minimum. Concave down, so I must be at a maximum. But there's these other surfaces that are concave up in one direction and concave down in the other. So I'm going to draw my favorite thing again, which is this guy. So this function has the property, can I draw this? This comes down, this comes over, this comes down. This is a parabola in this direction. So this comes down like this. If you look at this point right here, that point has gradient f equal to 0. That's not a maximum, and it's also not a minimum. And if you look more closely, there's a parabola here that's concave down, and a parabola here that's concave up in the other direction. So that is a critical point that is neither a maximum nor it's a minimum. In fact, if you guys remember from 241 or any other sort of multivariable function theory, this is called a saddle point because that shape that I just drew looks like a saddle, something you could sit in, right? And so in a saddle point, we have critical points that don't correspond to local maxes or local mins. And they're not inflection points either, right? We have one kind of concavity in one direction, sort of that parabola up, and a different sort of concavity in the other direction where it's concave down. And so when we build our idea, we want to build it in a way where we can somehow come up with a second derivative test that can see each of these cases. So we need to come up with a second derivative test, some way of using HF so that we can detect local maxes, local mins, and also saddle points. And that's where we're going with this. So we're going to use our degree 2 Taylor polynomials to study optimization of functions, finding local maxes and mins, which is a really important thing to be able to do in application. Okay, that's where this is headed. And that's it for today. Any questions about any of this? Thanks for putting up with the virtual class. I appreciate it. And yeah, I'll be back in regular class tomorrow. But thanks for hanging out, guys. Andre.
Yeah, Professor, I had a small question about like previous stuff. So
sure.
I wanted to double check. So S dot is essentially just length of speed vector, right?
Yes. So S dot means a time derivative. So if you have S is equal to the length of the velocity vector, you got to be a little bit careful here. S is the length of the velocity vector, right? S dot is the derivative of the length of the velocity vector. So it's not the derivative of v with the norm attached to it. You compute the length first as a function, and then you take the derivative of that. And so typically that will involve square roots.
Oh, so you're like, okay, that's okay, because it wasn't like my answers were not getting, I wasn't getting the same answer.
Yeah, so if you take the derivative of v, you get acceleration, but S dot is not equal to the acceleration. You got to be a little bit careful with that. S dot means find the linear portion of the velocity, which is its length, and then take the time derivative of that. So you can think
Okay,
about this
so
as
then-
this is equal to d by dt of the square root of x prime squared plus y prime. Hold on. It's the derivative of the square root of dx dt squared plus dy dt squared plus dz dt squared, right? So you do this first and then you take the derivative.
Okay, I see. Another quick question. So, like in the last problem, when we had to calculate linear acceleration and turning acceleration,
Yep.
we had like two formulas. We had like first formula, and then it was simplified. So we have like s with 2 dots t plus s1 dot dt over dt, and
Yeah,
it simplifies to s double dot t plus ks squared n.
That's the one
Which-
you want. That's that's much easier to compute with if you just do
Yeah, that's
s
last
s dot squared t not s dot squared, sorry, s double dot. Look at me like totally remembering these. S double dot t plus s dot squared kappa n. Yeah, this is the linear part, and this is the turning part.
Okay, I see. I see. Okay, thank you, sir. So, and finally, I turned, I like put the homework into your thingy. Is it okay?
Yeah, that's totally fine. I mean, that's all stuff I'm gonna have to deal with tomorrow, so don't worry about it. Yeah, that's cool.
Okay. Okay. Thank you, sir. Well, yeah. Get better, or your kids, I wish would get better faster. But yeah, thank you, sir.
Thank you.
That's it. Goodbye.
All right, Steven, what's up?
I had a question also about a previous lecture.
Okay.
I could have written it down incorrectly, but the way I wrote my torsion equation when we went over in class was the derivative of the binomial vector with respect to t
Yeah.
is equal to that stuff. Should it be to s? Because I remember doing the homework, and I think they were doing, or at least some of the solutions were using the derivative of the binomial.
I
binomial
can,
vector.
yeah,
with
let me
respect
go.
to s.
Yeah, let me go look. It's ds. It's a ds derivative. It's a ds derivative. Yeah.
It is ds?
I just
Okay.
wrote I wrote that down. I wrote that down incorrectly. Yep.
Okay, so then to calculate torsion, we would just like calculate dB dt divided by ds dt is
Exactly.
equal to like
Yeah,
the negative torsion times the normal vector.
Yeah, because if you have dB,
Okay, sweet.
dB ds, it's the same old chain rule argument. If you divide this by ds dt, then you really secretly what you just did was dB dt times sorry, wrong. It should be multiplied, right? If dB yeah, because dB ds times ds dt is equal to dB dt. So that means, yeah, to actually compute dB ds, the easiest way to do it is to compute dB dt and then divide it by ds dt. I mean, you should see that this ds dt is just all over these computations because you're constantly normalizing out the velocity vector. That's really what's going on there.
Yeah. Okay, sounds good. Thank you so much, Professor. I hope your son feels better.
Thank you. Anybody else? Hi, too.
Hello.
Hi, Trinity.
I just was wanting to. Sorry I emailed you last night in the midst of all your chaos.
Dude, that's cool. I mean, you sound like you've been kind of dealing with it too. So
Yeah. So should I try to have the homework to you by the end of the week, or I can guarantee it to you on Monday? 100%.
I mean, you've been out for a couple of days. You just, I mean, you've been out and now I'm out. So if you don't have it by tomorrow, just make sure you got done. Just get it in by tomorrow, by Monday. It's totally fine.
Okay, thank you.
Yeah, just don't. Yeah, just don't get behind on the new stuff.
No, yeah,
that's come in.
definitely.
Cool.
And so could you do you have office hours tomorrow or no?
I don't, but I was planning on actually scheduling something on Friday to make up for the fact that I couldn't make it today.
Okay.
Tomorrow's hard because tomorrow I have to. Normally the childcare that we got doesn't. I can't leave until around 1, so I don't have that morning time usually on Thursdays. But I'm gonna try to post something for an office hour on Friday.
Okay, awesome.
All
All right. Well, thank you for your understanding. Hope
Yep.
your kid gets better.
Thank you.
All right.
See
Bye.
ya.